everyone. Welcome to Risk Roundup. Over the years, encryption has become a constant in our daily life. While it has become an indispensable part of our digital life, security in cyberspace is still a complex challenge. Now, if we look at our everyday life, each phone call, email, chat, video calls, software updates, e-commerce, and so much more that we are doing in cyberspace, we put our faith in math for security. But the systems based on math can be hacked. So although mathematical models do encryption, they will likely not give us the security we need. For security in cyberspace, and because of cyberspace, in aquaspace, geospace, and space, we need something more substantial to replace these mathematical models. Now, with growing computing power and quantum computing, it seems quantum cryptography, quantum encryption, and quantum cybersecurity give us a likely alternative. Now, we are already witnessing the quantum properties of matter and light being applied to build quantum satellites to quantum internet and quantum cybersecurity. So as actual devices using quantum properties begin to transmit information over considerable distances, it is essential to evaluate quantum encryption for cyberspace security. Now, in search of greater security from code breakers, it seems a new generation of code makers are turning from math to physics by exploiting quantum mechanics laws to send provably unhackable messages. Now, we are honored to welcome one such code maker, the visionary architect of quantum cybersecurity, Dr. Vikram Sharma, to Risk Roundup. Dr. Sharma is the founder and CEO of Quintessence Lab based in Australia. Welcome, Dr. Sharma. We are so very honored to have you on Risk Roundup and our Risk Group community. And I look forward to your presentation on your initiatives at Quintessence Lab.
Hello, Jayashree, and thank you for that context and warm welcome. It's a real pleasure to be joining you this morning, and I look forward to a short presentation followed by a discussion on exactly the topics that you set out in the introduction. So if you would like, may I share my
yes.
screen where I have a
please.
presentation here. Okay. Can you see that screen okay?
Yes.
Terrific. Well, what I thought, Jayashree, we could do in our time together is break up this presentation into perhaps 4 short segments. The first is perhaps to start with a historical context around quantum science, which over the last 110 years or so has really developed in a tremendous fashion. And then perhaps, to your point about the advanced computational powers, have a short 101 primer, if you will, on quantum computing, and indeed some of its applications. And then thirdly, turning to the threat that such advanced computational power would present to cybersecurity. And then finally, closing with a look at some of what we can do to achieve a quantum safe posture, and perhaps some of the risks that are current open items of debate amongst the quantum and cybersecurity communities. So kicking off with that, if you look at quantum science, well, even preceding quantum science, around the end of the 19th century, so late 1800s, we really thought that we had a good understanding of the world around us, from the motion of the planets to the falling of an apple, with the laws of Newton, Galileo, Maxwell, and so on. We really thought we understood the world quite well. And in fact, capturing the feeling, the sentiment of the time, it's an interesting quote from Lord Kelvin, from the Kelvin temperature scale, where he said, everything that needs to be discovered in science has been discovered. All that remains is more and more precise measurement. So there really was this sense that we had a good feel of the world around us. However, even within this context, there were a few problems that couldn't be answered or we didn't have good explanations for. And one of them was the so-called black body radiation problem, which concerned the spectrum that we saw from stars. And using the laws that we had, so-called classical physics, we just couldn't explain why we were seeing the patterns we were within the spectra. In 1901, we found a gentleman who came up with an explanation for this. His name was Max Planck, an eminent physicist from Germany. And he came up with this explanation, but in doing so, what he had to assume was that energy emitted in discrete quantities. You couldn't have any value from 0 to infinity. You had it in very discrete amounts, which he went on to call quanta, which gave birth to the field of quantum physics. And in the succeeding decades, amazing physicists such as, of course, Einstein, Schrödinger, and others really gave more evidence in support of this idea of quanta of energy and giving rise to the field of quantum physics. And over the last 60, 70 years, we've really leveraged these ideas into all kinds of things which are absolutely, unthinkingly almost a part of our everyday lives. So semiconductors, of course, so embedded that we don't even think of them. But if you think about the latest chip from AMD, I think it's called the Gen Z chip. On that, it has 40 billion transistors on a single chip about this size. So quite remarkable, the progress that we've achieved there, which has been so transformative for our everyday lives. Of course, you have lasers so embedded in a multitude of applications around us. GPS, you may not be aware, but to achieve a location, what our cell phones, for example, do is they reach out to 2 satellites, and they basically triangulate our location using the time it takes a signal from one satellite vis-a-vis a second satellite to come to us to determine very accurately where we are located. But to achieve this, you actually need highly accurate clocks on those satellites. And those clocks are atomic clocks leveraging quantum effects as well. And of course, yet another application is MRI, so fundamental to our everyday life. So while the physics might be complex, these technologies are very much a part of our everyday life, so-called products of the first quantum revolution. Interestingly enough, over the last 20 years, though, we are entering the second quantum revolution. And in the first, what we were doing was taking effects in the natural world and leveraging those passively. In the second quantum revolution, we are able to actively engineer quantum states that don't exist in nature. So if you want to think of it like we create supermaterials, which might have special properties on strength or rust resistance or lightweight, in the quantum world, similarly, we're able to create new quantum effects that don't exist naturally. And as a result, we're seeing a whole host of new capabilities coming to the fore. Quantum computing, you might have been hearing quite a lot about that with IBM, Microsoft, Honeywell, and of course, Google really leading the charge and giving us unparalleled computational capabilities. Quantum sensing, a lot of work going on there to be able to detect objects with unparalleled precision. Consider looking for submerged objects around our coastline for national security, or looking for oil and valuable minerals with much greater precision than what we could previously. Quantum imaging, think about detecting cancer at the single cell level, and perhaps then sending out a nanobot at some point in the future in our bloodstream and eradicating cancer forever. incredible step change technologies. But really, the subject, I guess, of our conversation today is the applications to security and the dramatic changes that quantum can bring there. In fact, we at Quintessence Labs have a catchphrase here of using quantum to fight quantum in the field of cybersecurity. So with that, very quickly, without going, you could spend hours on the topic of, how quantum computers work and their applications, but very quickly looking into what differentiates them from a conventional computer. Conventional computers, once I add more computers, for example, if I wanted to search a database and looking for a particular name that started, or I had a number, let's say a phone number, and I want to see whose name it corresponded to because I'd lost that name. If I had one computer, I'd search all the entries starting with A, going to B, C, and so on all the way through to Z. And hopefully in that search, I would find the name that matched the number, the phone number that I had. If I want to go faster, I'd get two computers. One, I'd search A to L, and in parallel, I'd search from M to Z, and so on and so forth. So every time I add a computer, I get a linear speed up in my search process. And you could represent that by, if you want to think of it this way, about pointing at the North Pole or the South Pole on the globe, if I was sitting at the center of the Earth. And one could represent a digital 1 and the other a digital 0. And that's how it is in a conventional computer. On a quantum computer, I could represent multitude of values at the same time. So instead of pointing just to the North Pole or the South Pole, one of those at any point in time, I could be pointing to both of those, including London, Tokyo, and Sydney simultaneously. So what this gives us, and this is an idea called superposition in the quantum world. So what this gives us is the ability for exponential speed up as opposed to linear in the classical world. So if I have one qubit, which stands for quantum bit instead of a bit in the conventional world, I could have a 0 or a 1 at the same time. So if I had one qubit, I'd get a speed up of 2. If I had two qubits, I could have 0, 0, 0, 1, 1, 0, 1, 1 all at the same time, and so on and so forth. But the thing to note is every time I add a qubit, I'm doubling the power. So I'm getting not a linear, but an exponential speed up in my processing capacity. And it is suggested once I get to 20 or 30 qubits, because I'm doubling each time, that will be as powerful as our best supercomputer on the planet. And if we got to 200 or 300 qubits in one device, and it's not a trivial technical challenge, but feasible, that 200 or 300 qubit quantum computer could have equivalent power to all the computers on the planet today. So remarkable, remarkable step change possible there. And of course, big investments going on globally. China, it's estimated, is putting in over $10 billion. Europe, €1 billion. US recently was signed by a presidential act, $1.2 billion national quantum initiative, and so on and so forth. Very major multi-billion-dollar investments going on. And in the private sector, venture capital has jumped in. I think that number is over $1 billion, perhaps well over $1 billion that venture has put into various quantum startups, and some tremendous progress being achieved there. And applications, range from big data and AI and machine learning to optimization. So this issue of if you had 15 locations to go to, what's the best routes to take between those? Once you get to about 15, our best supercomputers, it's too complex a problem, cannot solve it. Interesting enough, UPS have suggested if they could shave 1 mile per day from the delivery of their packages per truck, it would add $50 million straight away to their bottom line, just by optimizing that. So that's that problem. Amazing advances in biomedicine, financial services, and indeed cybersecurity. But as we look at that, and of course, great advances being happening by Google and others. But the threat to quantum computing today, it's suggested, sits within the next 5 to 15 years that we will see a quantum computer at the right scale, which could impact our e-commerce that we're using today, which relies on something called the PKI, or public key infrastructure. But what we're seeing is that these so-called harvesting attacks, where I'll store sensitive data today and decrypt it at some point later in time, when it may still have some value, it's understood are occurring already today. And then you overlay that with the fact that when you look at changes in security technology, it takes you some period of time, multiple years, to be able to transition to new technologies. So that really suggests that we have this threat to cybersecurity potentially today. And what is that? I won't go into this in great detail, but much of our cybersecurity today, as I said, around public key infrastructure, relies on the fact that if I give you two large prime numbers, and a simple example is given here, it's 165,181, and another one being 417,953. And I say, Jayashree, could you multiply these, please? And you'll get your pocket calculator, and in probably 2 or 3 seconds, you'll give me the result, which is 69 billion, 37 million, etc. But if I gave you the reverse problem, I said, here is a number which is 69 billion, etc. Can you please tell me what two numbers were multiplied together to arrive at this? That's a tough problem. It will take you quite a long time. And we rely on exactly this asymmetry, where it's easy to go in one direction, but hard to go in the other direction, to achieve a secure e-commerce today. And in this, using our current key exchange, such as RSA 1024 or RSA 2048, it would take thousands of years for our best supercomputers to reverse these out. But a quantum computer could reverse this very rapidly, in a matter of seconds or certainly minutes, using an algorithm called Shor's algorithm. This means public key exchange, what we use for e-commerce today, will no longer be safe. And how long will this take to do? So a gentleman at the University of Waterloo in Canada, Michele Mosca, has given us quite I think a neat, simple mechanism to think about this. And he relies on 3 parameters. So how long does the encryption need to be secure? That's often legislated, right, for health data or financial data, and indeed many sovereign secrets. So we determine that X. Y is how long it takes you to transition to new secure cybersecurity technologies. And Z is how long, in your estimate, within that sort of range, I think we suggested 5 to 15 years, do you think it will take to achieve a quantum computer that will threaten this? So this gives you a nice little mechanism to think about how quickly you should move on this. So what should we be doing about this? So here's a quick little checklist, if you will, Jayashree, of 5 things that we think you should be thinking about today. First of all is just basic good cyber hygiene. So identify your systems that actually perform cryptographic operations. And particularly within those, look at those which use public key infrastructure, and those could be vulnerable to quantum attack. And also identify those secure communications links which carry critical communications. Keep a watching brief. So there's some work that's going on by NSA and NIST at the moment to identify new algorithms which are, we contend, will be safe to, or resistant at the very least, to quantum attack. And where possible, start to use true random numbers as the building blocks of your encryption keys. And once these post-quantum algorithms are deployed, it's suggested that will be about 3 years from now. Be ready to implement those. And finally, use a quantum technology called quantum key distribution where applicable for your particularly sensitive links. So what are we at Quintessence Labs doing about this today? What you see here today is a product that we've deployed at a number of large banks around the world, with cloud service providers, with federal agencies, and indeed with the defense sector. And what this has is, instead of using software-based methods to generate true random numbers and encryption keys, it has the middle of your screen there. You see something about the size of a cell phone that sits inside of this appliance. It's the world's fastest true random number generator. It measures an effect called quantum tunneling, and it puts out 1 billion true random numbers per second, which feeds into a software stack which chunks up those random numbers into encryption keys. And we have something called crypto agile key management, so that we can use the encryption that we're using today, but it's well placed to transition into new ciphers that NSA NIST will suggest in the next 3 years or so. And the second piece is this emergent technology of quantum key distribution, which puts on its head, instead of using complex math to protect the exchange of encryption keys, it uses the laws of physics. And very simply, what we do is we do something like AM and FM on a laser. And if I'm sending that to you, Jayashree, and somebody tries to intercept it, at the quantum level, what happens is if you look at something, you change it. So therefore, we will know and we can discard that key. However, once we've established that nobody's looked at it, we can use that encryption key confident in the knowledge that nobody on the planet, even the universe, has a copy of this. So that's a sort of very quick background. What I would leave you with was a very interesting thought from a gentleman called Roy Amara, who used to be a futurist at the Stanford Research Institute. And I thought he left us with this sort of quite instructive thought that we tend to overestimate the effect of a technology in the short run and underestimate its effect in the long run. And I think Bill Gates put a little bit of precision around this, defining short run to be 2 years and long run being 10 years. But this does leave us, and maybe this will sort of go into our conversation that follows, with a few open issues in terms of sort of cyber risks that we see at the moment. And I'd be happy to drop into a conversation as we now move forward, Jayashree.
Great. That is certainly very informative and intriguing, and very, when I see where this could lead, it is certainly going to be an entirely new industrial revolution that could emerge based on the advances in quantum physics and quantum mechanics. So this is certainly, very, very exciting time. And congratulations on all that you have achieved and all that you are striving to achieve. So from your assessment, where do you think quantum cybersecurity draws its strength? How do you think it will help nations and protect our collective future? Because that's what I'm really concerned about, our collective future.
Absolutely, Jayashree. If you look at the way that our digital lives are increasingly playing out, not only are they reliant on cybersecurity measures that we as individuals, enterprises, or as governments implement, but there's a lot of shared infrastructure on which we're reliant. If you think about the public key infrastructure, this is something which has collective governance and collective ownership. We really need to think about how, in a future where we have a quantum-enabled adversary, will we ensure that our digital lives and our digital exchanges continue to be safe? So to your question, quantum cybersecurity really draws its strength from two areas. One, as we just briefly touched on, is ensuring that all of our different kinds of security credentials like encryption keys, PIN numbers, digital certificates, and so on are all constructed from true random numbers. And you can only achieve true random by measuring a physical effect. Today we try and simulate them. We get pseudo-random through software, but advanced computational power in the future could find patterns and therefore weaken our security. So one of the areas that quantum can really contribute is by, in our case, we measure an effect called quantum tunneling to produce those billion random numbers per second that I talked about. The other areas Yeah, so really, critical, important, foundational input into cybersecurity. The
Yes.
second is around that exchange of keys. As I said, at the moment we've been using complex mathematics to protect it, the exchange of those keys. So if we use quantum effects with this idea that if I'm sending a key to you and somebody tries to eavesdrop on it, hack into it while it's being sent, by the laws of physics, we will know. So it kind of changes the paradigm. So these two elements, coupled with the ability to manage encryption keys at a scale, as we move into a world where we have millions or hundreds of millions of keys, especially as we move into the Internet of Things context, that what we call crypto agility will be critical. So true random numbers, quantum key distribution, with the glue of agile key management is, I think, what we will really need to support and protect our digital futures.
Yes, yes, I agree with you. The challenge that I see is that each country is at a different maturity spectrum in terms of their infrastructure. So, if we do want to bring this kind of change on a global level, then there needs to be a parallel progress in the infrastructure for each country, and that's going to be a very complex challenge because a lot of geopolitics and a lot of resource constraints will come into play, and that is a concern for our collective progress that we are trying to make for the entire human species, human civilization. So while laws of physics says quantum cryptography is unhackable, do you think it is? And do you think we need a better control of quantum cryptography over quantum cybersecurity systems?
Yeah, really interesting points you raised there, Jayashree. Certainly, if you look at it at the theoretical level, the laws of physics do assure you that those keys will be exchanged absolutely securely. But as you implement any theory, you need to realize it through some physical devices. And where weaknesses and where we need to ensure that the weaknesses do not exist is as we implement these laws of physics, that we implement them correctly and robustly so that we don't create, if you like, avenues for adversaries to exploit in our realization of those products and those technologies. So that's where potentially you could see attacks to it, but if they're correctly constructed, you would expect that those should be very secure. But that does bring us to the follow-on question, which is, what if malicious actors could gain access to exactly these types of technologies? And you may have seen that even without the quantum safe methods to exchange information, a lot of debate is currently going on globally about how do we ensure that we respect the privacy of individuals while at the same time keeping us collectively safe by ensuring that malicious actors cannot use this for I guess, effects which would impact our collective safety. So that is really an open question and one that merits significant debate around, what is the right balance to achieve between keeping us collectively safe and individual freedoms, and what are the right mechanisms and technologies to achieve that balance.
Yes, very true. That is a complex challenge, and the adversaries are growing in number and size, and they have all the advanced tools that we have. So that is going to be certainly very challenging for the security professionals to make sure that they can protect all the systems. And we are going to witness the warfare in the electromagnetic spectrum. So there is no doubt about that. That quantum technologies are going to be quite impacted. So what is revolutionary about your organization, Quintessence Labs technology and approach, and how would your system work in theory and practice? You gave a great background, overall, but I would like to know more about your organization's approach and efforts in solving these problems.
Indeed. So the approach we've taken is that in the adoption of quantum technologies, we really feel that an integration of these unique frontier technologies of quantum with existing cybersecurity software is the best way for its adoption, indeed technology insertion today. We have always thought that an approach which says, well, sorry, you need to, I guess, retire existing investments, which are hundreds of millions or billions of dollars, would not be a very good path forward. So we've spent a lot of time thinking about how to integrate and interface these advanced technologies with existing cybersecurity infrastructure. So our products and solutions today really have an embedding of quantum effects with conventional cybersecurity and are designed to drop in to conventional data centers very seamlessly and not only provide you new advanced capabilities, but indeed improve the return on investment on infrastructure assets which are in place already. And we achieve this through those three mechanisms that we just touched on before: high quality, high speed, true random numbers, quantum key distribution for those very sensitive links where you want to particularly protect the exchange of information, and then key management and the ability to enforce data security policy as the glue that brings all of this together and allows it to interface with existing capabilities.
Yes, sorry, you are absolutely right. The politics of investment is always very complex, challenge to manage. So what is the impact of the proposed technology promise? And besides making hacking difficult, while quantum cybersecurity offers many, many advantages, what benefits does your initiative bring that you think that your competitors or other, market advances, they are not able to meet that?
Yeah, the approach to that, Jayashree, that we've taken is that we look to address some of the critical cybersecurity challenges that organizations are facing today while preparing them for a quantum safe future. And when we look around the cybersecurity landscape today, one of the big challenges enterprises are facing as they move to this idea of so-called layered defense. Historically, we've tried to put these big walls around the IT systems, firewalls and equivalent, to try and keep the bad guys out. But what we're seeing is that increasingly the bad guys do find little chinks in our walls and they're on the inside of our systems. So most enterprises are moving to this idea of layered defense, multiple layers of cybersecurity working in concert to give you a very strong cybersecurity posture. Within this framework, one of the strongest layers you can implement is enterprise scale encryption. So now doing the encryption piece is actually relatively trivial. What most enterprises are challenged with is how do you manage, with the right performance, with the right controls, with the right redundancy, millions or hundreds of millions of keys? And how can I get this to operate in a very heterogeneous IT environment, which most enterprise data centers will have a multitude of different vendors, hardware and software. And it's non-trivial to be able to seamlessly interoperate with all that mixed set of hardware and software. So that's a challenge that we solve today. We have true random numbers and advanced key management, which operates at scale, high redundancy, high performance, and allows you seamless integration with this very heterogeneous hardware and software environment. But it does so in a way that we just mentioned a short while ago through crypto agility. So we can use the encryption methods we have today, but as NSA and NIST announce the new ciphers 2 to 3 years out from now, we can do a rollover to those new systems without requiring a whole change of the underlying infrastructure. And this, in the way that we've packaged it up and deliver it, is globally quite unique.
Yes, no, that seems very much essential because, you do need to speak the same language for all the different hardware software components that you are trying to integrate with. And it, like you said, the layered approach has to be there. There are so many different challenges at so many levels, and we are not going to face only one adversary. We may face adversary in number and size from all different directions. So there is a need for very complex, integrated, interconnected security system, or defense system, I would rather say, to protect our assets in cyberspace, aquaspace, geospace, and space. So suppose we want the entire cyberspace and all data and communications across nations secured. What is required in terms of hardware and anything else needed to move forward with quantum cybersecurity? Because there's so much advance when we see with the software, but when we look at the hardware, we haven't made a lot of advances yet.
Yeah, again, I think we're right at that point. And on that chart, like I showed you from Michele Mosca, it is something that I believe many enterprise chief information security officers are now starting to look at very carefully. And indeed, boards of directors really need to be aware of the potential risk of not moving in the right time frame. I would say that we do have the luxury of time now, and if we develop well thought out strategies, we can be well prepared. However, should we get somewhat complacent and decide that this is not a problem for today, I do believe that we could be exposed to significant risk. So we're actually doing some work with the World Economic Forum. Quintessence Labs was fortunate to be recognized as a global innovator about 3 months ago, and along with a number of government and defense agencies in starting to plan for what this future cybersecurity architecture and infrastructure could look like. And we really feel that it will be a hybrid of advanced software-based mechanisms, so these quantum-resistant algorithms that are being worked upon, and quantum technologies such as the ones that we've just talked about. And in implementing these, I think we'll come up hopefully within the next 12, 18 months with reference models that have hardware such as what I just showcased to you, our Trusted Security Foundation, or equivalent products from other companies, to really manage these encryption keys very well, generate them from true random numbers, and protect them robustly, because in the end, these encryption keys will be the essence of what delivers us security in the future.
Yes, no, congratulations on the recognition by World Economic Forum. That is amazing, and you rightly deserve that. And the point that you made about the discussion, we have to have a collaborative discussion within and across nations with all the components. See, we are developing all these technologies that requires extensive collaboration at all levels, individuals as well as entities across NGIO. That means nations, is government, industry, organizations, and academia. Everybody needs to be involved to be able to ensure that we are going to be able to meet the complex challenges of tomorrow. And in terms of that, we are going to be able to meet the necessary transformation wherever it's required, hardware, software. And like you said, it's going to be hybrid, and I agree with you, it will need to be hybrid approach. So I'm glad that you are taking actions on all those initiatives. But do you see anything limiting the use of quantum cybersecurity? I mean, it could be hardware, it could be software. Do you see anything limiting?
No. I suppose that there's probably two elements to that, Jayashree. So the first is that some of these technologies could be construed as being sensitive and in the national interest. So we can start to see certain levels of controls around those capabilities, and whereby nations may seek to gain those benefits for their own sovereign purposes. So that could impede a global diffusion of those technologies. The second is, of course, the true random number generation technology is well mature, so I think we could see broad applications of that. Quantum key distribution is still maturing, and at the moment it is expensive and requires hardware of some significant capacity and size on each end of the communications channel. So that over the next few years, I think, as suggested by Roy Amara, that it will continue to mature. And so I think perhaps just the time frame to mature out that capability, which may be a few years till it gets down to a level where it can have broad adoption, is perhaps the other factor that we would need to consider.
Yes, yeah, I do agree on that. So, as the quantum property of light excites security professionals like you and I, and many others, what different applications do you see emerging? I mean, you did mention about that we will first see some development in the confidential areas like security for defense agencies and military and all. But where else do you see commercial applications emerging?
So, of course, security we've talked about at quite some length, but other areas which they could have application in is within, I think we touched on it briefly earlier, is it within sensing? So to be able to sense in various applications with much greater precision than we can today. And the other area would be in imaging. So, which would immediately have applications in medicine and our ability to diagnose diseases much earlier. So, those are certainly areas which are the subject of much research all around the world at the moment. And I dare say, within the next handful of years, we'll start to see some early applications of these technologies in some of those adjacent areas.
Yes, so that is for the healthcare sector. You mentioned that and you explained that very well in your presentation. But when we see the security sector, apart from the cybersecurity, if I may, rephrase, it's the digital space. Where else do you see the applications emerging other than the security, space?
So we've got security. We've talked about imaging. We've talked about applications to sensing. Of course, the other is in quantum computing. And of course, there we're seeing a lot of work happening all around the world, but that's not so much looking at light. That's more looking at creating unique quantum states and keeping them well isolated within these different systems being studied, but some of the most promising ones that could have a broad application are whether we can achieve this within silicon. And that then would allow us to very rapidly create quantum computers at scale. But of course, those are emergent research. And again, depending on where your estimate lies on the rate of progress, and developments at frontier technologies are not linear like engineering problems. So you can't actually predict with great accuracy where or when we might expect to see these occur. The innovation occurs with discontinuous jumps. And, but, we have seen, given the weight of investment that we talked about a little earlier, some tremendous advances occurring just in the last couple of years. And we expect that rate of advancement to certainly continue and maybe even accelerate as we look into the next 2 to 3 year time frame.
Yes, I agree with you. And I hope that each country is focusing on, making the necessary investment, because when we look at Chinese scientists, they've already built the first quantum satellite network. So when we look at that, what security challenges do you see emerging as we work towards building on the feasibility of quantum communications from space? And that is probably not very far from, where we are.
A really interesting question, Jayashri. So yeah, the Chinese satellites really was early stage demonstration, if you like, really just showing the art of the possible. But certainly an important milestone in the development of secure satellite comms. And what it also does address is that at the moment, quantum key distribution, because these signals are very small at the quantum level, if you use optic fiber, over a period of some distance, let's say 50 or 60 miles, the signals degrade. So you need a station to measure that effect and then recreate it and then relay it on, which means that to achieve intercontinental distances would be challenging if you need these repeaters every 50 or 60, even let's say 100 miles. So a mechanism to achieve transcontinental or indeed intercontinental distances is to relay these quantum keys via satellite. As you seek to do that, you do encounter a number of technical challenges as you try and make your way through the atmosphere. Let's say you have a ground station that's beaming a quantum signal up to satellite. There are a number of atmospheric effects which will degrade that signal. So a significant amount of research is going on into how can we get these very delicate, if you like, quantum signals successfully up to satellite and then relay them down to ground, potentially at a location thousands of miles away, so that now you have a secure key exchange between two locations very geographically dispersed. So certainly this is an area of great research, and we expect over the next 5 to 10 years that significant work will continue. The Europeans are also quite advanced, so the EU has a lot of work going on in space quantum communications, space-based quantum communications. And we, in fact, ourselves as Quintessence Labs have been working with a UK-based company that is looking to put up some quantum-enabled satellites in the next couple of years. So certainly a very exciting excuse me, area of research where we do expect to see significant progress over the next 5 to 10 years, which will then be supportive of global quantum secured communication networks.
Absolutely, absolutely. I agree with you. And it seems when we talk about space, the time variable also will be playing a much bigger role in how the quantum, transmission happens, how we are able to send those signals, to space and then, from satellites to, here. So it's going to be very interesting what new advances emerge, in the coming years. And I hope that, we can talk again as you make more advances and your organization, comes up with some more solutions that can protect the future of the humanities. And it seems that the future of code makers and code breakers is entangled. And it may be quantum on both sides, right? We are going to see quantum on both sides. So that's going to be very fascinating time. So thank you so much, Dr. Sharma, for participating in this roundup today. We appreciate your thoughtful insight into quantum cybersecurity, and our global viewers and listeners would benefit tremendously from what you had to say today. And as a result, this Risk Roundup Dialogue has been of service. We thank you for that.
Thank you so much, Jayashree. Really appreciated the opportunity to participate.
Wonderful. Thank you so much, Dr. Sharma. So Risk Group is a strategic security risk research platform and community. And through the Risk Roundup initiative, Risk Group and I are on a mission to talk with 1 billion people, innovators, scientists, entrepreneurs, futurists, technologists, policymakers to decision makers. And the reason behind this effort through this Risk Roundup initiative is to research, review, rate, and report strategic security risk facing humanity. This collective intelligence effort is essential to understand where we need to focus on our collective security and what destructive forces we need to be mindful about. Thank you for being part of the conversation. And until next time, I'm Jayashree, host of Risk Roundup, signing off. See you next time. Thank you.